Hi, good morning, and welcome to the Hitchhiker's Guide to the Cloud Native Stack. As usual, I have forgotten my towel. By the Hitchhiker's Guide, you should always be wearing a towel. But for some reason, I always forget at the hotel. Well, never mind. My name's Leander, and I'm happy to be your host. Thanks for joining the session. Lots of technology to show you within the next 50 minutes. Just briefly about me. Yes, this is me here. My name is Leander Reimer. I'm a chief technologist and principal software architect. I do work for Kuavia. We are a small software project house located in Munich and Mainz. I do live in close to Munich, close to the Alps. I'm a passionate developer and architect. I realized that I have more than 20 years of experience now. I turned 40 last month. Had my first job with 15, I think, programming printer drivers in HYPERSCALE. So yes, that's a long time. If you do tweet, could you do me the favor and use this hashtag here? Our marketing department, our marketing ladies will love you for that, okay? In case you're interested in the slides or the code, you will find all of those on GitHub and on SpeakerDeck. Nowadays I realized, well, developing, yes, maybe on the couch in the evening. What I do most of the time is this here. So I do work for BMW, for example, quite a lot. I've been consulting at Allianz Insurance pretty recently, and all those big companies, of course, they want to go to the cloud. They want to know about this, well, this thing that's going on currently, this new modern way of architecting and building applications. And you might realize I'm this small white dog there, and people come to me and say, Leander, what's this microservice thing? Do we need those? What's this cloud? Do we need this? Please tell us about this. And of course, I tell them about, and of course I say, yes, of course, you have to do that. No, seriously, of course, something I say, well, it depends. And let's see on which factors this depends on. And I think the move to cloud-native application has, well, 4 main factors. There's probably several more. The one thing is the term hyperscale. Now, modern enterprises, they have new fancy ideas how to sell stuff to their customers, right? So they have new ideas, they have new features, they have more data, they have more clients, they have more interfaces, and this leads to, well, a lot of more scale that the systems you build need to cope with. So currently, those current applications we might have built in the past, they are not fit for this type of scale, for this web scale, traffic and data. So hyperscale is one thing. The next thing, of course, is anti-fragility. If you base your whole business on IT and on servers and on software, then of course those systems should not break, right? Otherwise you lose money. If you're an e-commerce platform and if you're down, then your customers will go to Amazon or wherever and not buy stuff at your place. So you cannot afford that those systems break, that your systems break. So they need to be anti-fragile. They need to be self-healing. They should not break. The next thing we see is that the software development is industrialized. You probably heard of all those terms here, DevOps and continuous delivery. This is about, developers being responsible from day one to putting the thing into production. It's about short release cycles. It's about continuously deploying your software into production. Not like every 3, 4, 5, 6 months. Maybe every week. Wouldn't that be nice, I know most of us are not Amazon, so we don't need 1,000 deployments a day, but once a week would be nice if you come from a 6 months period. So we need to change here. And another thing is this term OPEX saving. OPEX is an acronym for operational expenses. So what was the traditional way of scaling your application? Well, buy a bigger hardware, right? Buy a bigger servers. They cost a lot of money. And if you look at the resource utilization of those servers, it's usually like 10–15%. So you're wasting a lot of this hardware. And then suddenly, if you hit this spike in your traffic, then it might be that your current hardware is not enough anymore. So you have downtime again. So we want to be more flexible here. We want to save money. We want higher utilization and higher automation. So how do we do that? Well, 3 key principles. First of all, cloud-native applications are built and composed as microservices. Yep. They're packaged and distributed in containers. Second key principle. And the third one is, well, they're executed dynamically in the cloud. And we're all done, and this talk is over. Of course not. So, well, it's not that easy, as usual in software engineering, right? There is no such thing as a free lunch. If you want all this, well, I'm sorry to tell you, you have to do a couple of things. First of all, there are those 5 cloud commandments, okay? And you have to know them. First one, all things fail all the time. It's not from me, it's from the CTO of Amazon. And basically, if you have a highly distributed system, of course, things will fail. I'm not a big statistics guy, but if you have this 99.59s, and if you distribute this, then do the math, and you will see that you don't have this high availability anymore. So things will fail. Networks fail, servers fail, hard disks fail, databases fail. Everything fails all the time. And usually when you least expect it. So we need to focus on mean time to recovery and not mean time to failure. And this is something we as developers and architects need to, well, we need to shift our mindset here. Usually we said, well, another retry strategy, and yes, we can kind of work around this failure. Accept the failure, embrace the failure, accept it, and it's better if your server starts up in 5 seconds again. Let it crash, okay? If it's up in 5 seconds again, no worries. So we have to change the way we build the software. Hands up, who knows the 8 fallacies of distributed computing? Yes, the old ones. One hand, the unicorn. So they're really old. They're from 1991. Some smart engineers from Sun Microsystems, not there anymore, now Oracle. Well, they invented those, and those are things like the network is reliable. There's unlimited bandwidth. Oh yeah, speaking about bandwidth, I have a demo afterwards, right? So please be kind to the bandwidth, okay? So my demo works. Yeah. The network is secure. There is no latency. Yeah, right. Okay, so, and there are a couple of others, and you need to be aware of those if you build a highly distributed system. Scale out, not up. And then there's, of course, treat resources as cattle and not pets. This is this thing. You have servers, they have names. That's not the cloud way of doing it. If a machine is ill, the cow, you shoot it, you bring it to the butcher, you buy a new cow, okay? So you have a cattle farm. So, design principles. So, those are the things you should implement in your system. Design for distribution. Of course, we will be running containers, microservices, API-driven development, performance, responsive, concurrent, maybe resource efficient, or hopefully resource efficient. Maybe this changes the way, maybe you go to a reactive programming model instead of the old request response programming model to be more resource efficient. Automated dev and apps tasks. So for automation, of course, you need to have inbuilt endpoints in your application so that you can automate your application. I mean, this is not for free. If you don't do it, you don't have automation endpoints. Design for resiliency, fault tolerant and self-healing. Things will break, and if a dependent service breaks, this should not break the actual client service that's requesting there, okay? So have something like a circuit breaker, bulkheading, those are the terms here. Elasticity, delivery, important, short round trips, especially during development. If you have several moving parts and you're working on one microservice, obviously you sometimes need a bit of the ecosystem that this microservice needs later on. So what you want during development is really short round trips. Automated provisioning regarding the infrastructure, of course. And design for diagnosability, cluster-wide logs, metrics, traces. I mean, the good old monolith wasn't that bad, right? If there was a bug in the software, what did you do? Well, you open your debugger and you debug the whole thing and you find the error pretty quickly. If you're in a highly distributed system environment, well, how many debugging sessions you want to have open? 5, 6, and maybe spot the error? Okay, so you need some other ways of debugging your distributed system. Now, this is a lot to do, and of course you can go there step by step, and this is my advice you should do. Go there step by step. At level 0, you're cloud ready, you have no file system requirements, you run on a virtualized hardware, and you can be executed as a self-contained image. And remember, we're not always building greenfield projects. Usually we have brownfields projects, legacy systems, maybe not so legacy, but existing systems, what do you do with them? Can they benefit from this new world as well? And yes, they can. And you can easily lift them to level 0, quite easily. I've done that for Allianz quite a lot. So this is definitely possible and achievable in a short time. Level 1, cloud-friendly. So here you have loosely coupled systems, services can be found by name, and you adhere to the 12-factor app principles. So, cloud resiliency, now you have fault tolerance, resilient design, you have metrics and monitoring endpoints built in, and it runs anywhere and is not agnostic of the infrastructure. And then at level 3, then you have the cloud nativeness. Yeah, it scales dynamically, it reacts to stimuli, it scales out and in again, depending on the load. And you can even dynamically move the infrastructure and you will not have a service downtime. So this is the glory heaven of cloud nativeness. If you build a greenfield project, it should be rather easy to go to level 3. For brownfield, maybe you have to stop at level 2, but that's not that bad, okay? Now, this here is the anatomy of the cloud native stack, and what the cloud native stack does is to abstract all this distribution complexity from you as a software developer, or tries to. Down here, you have the cluster virtualizer, and this is concerned with how to decouple from physical hardware. Next up, we have the cluster scheduler, and this one is concerned with providing the right resources for your containers to execute. Next up is the cluster orchestrator, and this is concerned with how to run your containerized applications on top of everything, and it's about automating common, ops procedures. And you can see this as an operating system, if you like a cluster operating system. And on top of that, you usually have a cloud-native application platform. There are several out there. This provides the infrastructure, this provides some programming APIs that your application can be programmed against. Now, this is, the concept, and the big question is which technologies are capable or suitable for this stack. Well, a bit hard to read, loads of fancy icons on there. This is the cloud-native landscape. The Cloud Native Computing Foundation updates this one every time, and those are the different projects that are currently part of the Cloud Native Computing Foundation. And what you see here is you have those different, you have Cloud Native Storage, Cloud Native Runtimes, Cloud Native Networks, coordination and service discovery, scheduling and orchestration, different platform here at the PaaS level. So you can kind of go and, pick and choose the technology with the icon that is most appealing to you. What would be one option? Of course, not everything works together well, right? And the stack I want to show you today, this is one incarnation of a cloud-native stack, is this one here. We'll be using Spring Boot, Spring Cloud at the top level here. Orchestrate and scheduler will be Kubernetes, and cluster virtualization is the good old Docker, right? I mean, Docker is everywhere, so we have it as well. Good. So we have 4 phases of cloud-native application development: microservices, containers, composition, orchestration. So let's go. Microservices. Well, you could do a talk on microservices on its own. I tell you a fancy story. I think everyone knows Walmart. If not, it's Aldi, Edeka, things like this. So of course, what do they have? They have an e-commerce platform, and this is what it looked in 2002, right? So this usual shopping website, categories, you could buy things, you could register, you could search for items, and what did they do? Of course, they evolved it, here, new fancy UI, and what did they do? They added additional features, 2008. 2011, again, new UI, and what did they do? They added, again, new features. And then, sadly, bad news, right? First of all, they had a monolithic application that could only be deployed once every 2 months. I mean, that's quite short already, but not short enough for them. But this down here is even worse. It was unable to scale for 6 million page views per minute and was down for most of the day during peak events. So this is like the super worst case. No money the whole day, right? Customers go to Amazon. Bad. Now, they didn't go bankrupt, so 2016, this is what it looks now, kind of, and guess what? Additional services, so even more, but something changed. And good news now, well, they could do 1,000 deployments a day triggered by dev teams, 100% availability, new kinds of applications, IoT and mobile APIs, resource efficient, suitable scalability, all that. So the question is, okay, well, tell us, what did you do? So that's the big question. Well, the obvious answer, you might guess already, is, well, they decomposed the monolith. They chopped it up into smaller, manageable bits. Now, my student times are quite long over. I did my master's degree in 2000, and during my engineering courses, software engineering courses, I was introduced to a concept called software components. Who knows software components? Software components? The building blocks? Yes, one hand. The old ones, yeah, with the gray hair. Sorry, I do have them as well. So software components, those are the Lego bricks of your system. They have a well-defined interface, they hide their inner bit, they're your complexity unit, they're your design units, they're data integrity units. They should be cohesive and loosely coupled. So those are your software components. And what do you do with those design components? During build time, during implementation time, well, now they become your planning and team assignment unit and your development and integration unit. And now, it's the next bit, and this one is actually the only thing new with microservices, is, in my opinion, this last bit here, that you now have ops components, right? You have runtime components. They are your release and deployment unit, and they are runtime and scaling units. Now, what was wrong so far? Well, maybe nothing. I hope you did your homework here and at least had a well-structured monolith, right? So the only thing different was that so far we've taken all our development components and stuck them into one runtime component. And there you have it, your runtime monolith. But hopefully your software was well-structured, hopefully. And if not, then I advise you, do not do microservices. Because if you couldn't get it right during design time, what makes you think that your microservice architecture then suddenly works? So, there are different levels you can do that. How do you get from dev components to ops components? So, system level, monolith. Subsystem level, microservices, self-contained systems. Components, you have a good old microservices. If you go down even further, services, well, maybe we call them nano-services. If you go down even further to a method level, then you have your function as a service things like AWS Lambda, for example. I mean, this is almost the lowest you can go, right? And by doing so, you get quite a few benefits. More flexible to scale, runtime isolation is very good, right? If only one small piece fails of those, then the others are unaffected, hopefully. Independent releases are possible, higher resource utilization possible. But remember, there are some trade-offs, right? Latency, increased infrastructure complexity, troubleshooting and integration complexity. So this is what you have to think of. Now, what I could do now is implement a microservice, but I will not do that. I mean, Josh Long is way better at this as I am. So usually, this is our microservice here. It's a simple Twitter clone, right? If you're interested in the source code, it's here. But maybe a word about technology. I mean, Spring Boot, Spring Cloud is one super valid option to get things done quickly, right? If you're more in the JE world, well, never mind. Go to Adam Bean's sessions, and he shows you how you can implement JE-based microservices. If you're more on a .NET guy, .NET Core is good as well. If you're more a Go developer, then use Go. Okay, so microservices is an architecture pattern, and it's not about the framework you use to implement them. So, containerization. Well, you could go on and on about Docker. Well, basically, Docker is a virtualization technology, and what makes Docker different is, well, at the level at which it starts. You have those classical VMs, and Docker is not virtual machines. Okay, it's virtualization, yes, but not virtual machines. So here, classical VMs, quite heavyweight, long startup times, but good isolation. Okay, with Docker, well, you start at the operating system level, and you have your containers. So the private copy is really low, so basically only your application plus the bits it needs. Near zero runtime overhead and short startup times. So, from a developer's point of view, this is all you need to know. This is the Docker workflow. You start with a Docker file, you write the Docker file, you use the Docker build command, and using the Docker build command, you produce a Docker image. You can use the Docker run command to, well, execute your image, then your image becomes the container. This is like the living thing. You can start, stop, restart your container. You can even commit it and produce a new image. And once you're done, you can tag it, right? Tagging is like in your Git or SVN when you do a tag. So you can give it a specific name and tag. And then you can use the Docker push command to push it to some remote Docker registry or your local Docker registry if you have a Nexus, a company Nexus or something like that. So this is what a Docker file looks like. So you have a base image you base from, well, maintainer, this is just for, I did it. You have several run commands, and basically run commands are kind of executed in the, during build time of the image. It's like you can run an ordinary shell commands here. You can copy in your artifacts. You have environment variables, you can expose ports, and then down here, the command is basically the entry point into, this uses Docker to start your service. So here's some useful tips on using Docker. First of all, a Docker file is code, in my opinion, okay? It becomes an integral part of a code base, so please treat it that way, right? It's not a second or third class citizen, so it should be a first class citizen. This is how your thing gets executed in int, in prod, in dev, okay? So take pride and care when you do that. Know your base image. Size matters. For the Java people, don't use those official Java images. I mean, they're tremendously big. They're 680 megabytes. You have full Ubuntu distributions in there with every security leak you can imagine, right? I mean, if you need a bash, put a bash in. Then maybe use Alpine-based base image, put a JDK in, and then put your application in. Done. Not more. Small images. Chain run commands and use intelligent layering. This is especially important when you build the image, that the image gets built quickly. So have the JDK, then maybe use your microcontainer if you have one, and then on top you can kind of have an additional layer. Who knows Bob Ross? Bob Ross? Yeah, I always see him doing night, when he do the night coding. I think he's been an art professor, an American art professor. And look here, his hair, I try the same. And he always had the saying, to be a picture good, he always said, you have to work in layers, right? And that always reminds me of Docker, right? Where you have to work in layers as well, and you have to do them intelligently. Remove temporary variables, environment variables for important parameters. One image for all environments, really important, so that when it runs an int, you can be sure that it also runs in prod, right? So don't have different int prod dev images. Have one image. And maybe use some quality tools to check your Docker files and your images. There are some tools around which you can integrate into your Jenkins, for example, that tell you, hey, this image has security issues, fix those. Your layering is not very intelligent, change that, chain run commands. So there are a few tools out there that help you with this. Composition. Microservices need an ecosystem to run in, because one microservice is no microservice, right? One microservice is nothing else than a very small monolith. So what do you need? Well, you need a microservice chassis. This is how to execute your ops components. Well, you will need some fine-of-service discovery, right? So this one knows which service exposes which endpoints, and other people can go to the service discovery and say, like, where are the endpoints for service X? Configuration coordination, this is how to provide cluster-wide configuration and consensus. So cluster-wide configuration values, maybe some, well, I don't know, port values, hopefully not secrets, things like this. Service clients, how to call other endpoints resiliently and responsively. So maybe you use Hystrix as a circuit breaker, for example, if you're in a Spring Cloud world. You need an IPA gateway. This is how to access your endpoints from the outside. Of course, if you have a bunch of microservices and shitloads of endpoints, sorry for the swearing, then of course you do not want to expose all of those endpoints to the outside world. Okay? You need one central thing where you can do authentication, authorization, maybe some token management, maybe SSL termination. This is what you can do as an API gateway. And then the API gateway kind of forwards the call to the relevant microservices in your ecosystem. And last but not least, diagnosability and monitoring. Well, you want a way to detect and resolve operational anomalies. So, again, a wide choice. There's loads you can use. So up here, have a look at those landscapes again, which are out there, and pick and choose the one which you think, well, suits your needs best. Or maybe your customer already has some products or components some governance organization that pretty tell you what you have to use instead. Well, maybe. Now, if we extend our microservice now, this is what it looks now, and you see that it becomes more complex. Well, in Spring Boot Cloud world, it's pretty easy to extend the software. You throw in a few more dependencies and magic happens, and well, suddenly your microservice registers itself automatically with console. It can pull configuration values from the key value store of console. The actuator endpoints are there for monitoring and health checks, so stick in the actuator. So we use Prometheus here to actually call the endpoints. And we used a small API server called Traffic here that basically talks to console, says, hey console, which services are there, and then dynamically creates the routes for your microservice world. So this is the Docker Compose world, or the Docker world, and what I usually use is Docker Compose to spin things up, right? Remember, short development cycles. I mean, now you need console, you need a traffic, you need a Prometheus, you need to fire up your service A, maybe you need a service B. So how many consoles you want open? And always typing this lengthy Docker run command is sometimes quite tedious. Now, so my advice is use Docker Compose, and let's go here. So it's one line, Docker Compose up. Well, can you all read this good? So you see here, console starting up, our switcher service is coming up. Another microservice called switcher board is coming up. You see here, those are the log outputs from Spring Cloud, Spring Boot Cloud. So let this go for a while. Or what we can already try, HTTP get localhost 8080. We call our tweets endpoints. Q. Let's see. Let's see if things work and if the network's working. Yes. So you see down here, I called my Twitter endpoint locally, and this one proxies through to the Twitter API and does the call. I also have a really fancy UI, so localhost 81, I think. So this is usually the UIs I can produce. Okay, I'm kind of more the backend guy. I think an input field and a button is way more than enough. So this one is a microservice, a UI microservice, that actually calls the switcher service within our architecture and puts this here. Okay, back to the slides. 21 minutes, good. Orchestration. Now, this is now surely the most complex part. Now, we'll be using Kubernetes here for our demo, and I think this is currently the cluster scheduler where there's the most attention in the community. It's super actively developed, and well, it's rock solid stable. To spin things up, it's really easy, right? Either you use the shell version here. If you develop locally, you can use a project called Minikube that kind of fires up a small virtual box. Or if you're under Windows, you can use Hyper-V. So you have your small Kubernetes cluster for local development. You can go to the cloud, either to Amazon and spin up a Kubernetes there, or the Google Cloud, for example, where you have the Google Container Engine, which is a Kubernetes under the hood. Or you can use providers such as Giant Swarm, which provide you a managed Kubernetes cluster. You know, when you are a development team and you have no ops experience, right, then I urge you to go to some managed version like Google Container Engine or Giant Swarm, where you don't have to know how to install Kubernetes. But it's fun to do it at some point, just for the experience. Now, this is what Kubernetes kind of looks like. Here on the left-hand side, you have the master, and if you are using the command line interface, you will mostly interact with the REST endpoints of the master from the API server. So deployments, changing things, changing secrets, deleting, scaling, those type of things you do against the master. Controller manager, scheduler, here's an etcd server. This is like a distributed key value store. This is kind of the brain and the state of the Kubernetes cluster. And then on the right-hand side, you have here the worker nodes. And the worker nodes, they have a container engine, which runs your containers, or runs pods in this case. They have a kubelet, which is kind of the the remote control for the container engine so that the master can remote control the worker. And you have the kube proxy, which is responsible of, diverting the inbound traffic from your users onto the right pod in the right container. But from a developer's perspective, this is kind of, okay, it's nice to know that how this works, but if you're not an ops guy, then, you don't see much of this. From a developer perspective, I think those concepts and terms are even more important. So the pods are the smallest unit of compute in Kubernetes, okay? So a pod contains one or more containers, Docker containers, for example. And if you have more Docker containers in there, they share the same lifetime. So if one Docker container dies within the pod, then the whole pod dies, okay? Because you have a changing number of pods that, randomly maybe, they get rescheduled, they get scheduled on another node, they have an IP address, you will never talk to a pod directly. So what you have is the service up here, and this is an abstraction. This is your DNS name. This one has a DNS name. So if you want to talk to your microservice, you always do this via the service, and the service always knows how many pods are there of a certain type, and does like round robin or a sticky session, if you like, to the relevant pod, okay? So you always talk to the service. Now, there's a lot to do. What you usually do is you create a so-called deployment. This is like a nice abstraction. This is a way of declaring how many replicas you want, how many containers do I have, which environment variables do I need, all this. And it helps you at a later point to do rolling updates for your deployments, for your pods quite easily. And what this deployment creates is a so-called replica set. And the replica set will monitor your pods if they are alive, is one dying. Let's assume you want 3 pods running, three replicas running, one is dying, the replica set will know this and will restart one, okay? So it's the replica set's responsibility that always the desired number of pods is running in your cluster. And what you have is labels, so they are basic key value pairs. They are used to identify things within Kubernetes, okay? So you give your pods labels, and your service, you tell the service, this service, please match all pods with those labels. So this is how things work. This is pretty flexible. Now, single or multi-container pods, that's a question. Remember, so this is the question, how many containers do you stick into one of those pods? And, the answer is simple. If they both share the same lifetime, then you can stick them in one pod. For your microservices, it's probably good to stick them into several pods. But what you can do is like have sidecar pods that ship the logs out of this pod, for example, to some central logging, maybe. Yeah? So you can, of course, there are use cases where it's sensible and useful to have multiple containers in one pod. Right. So if we deploy this now to our Kubernetes, then this would look like this. We have a deployment for traffic, we have a deployment for our switcher service, we have a deployment for console, and a couple of other things. They here talk to Kubernetes, and all is happy, dandy, fine. Now, for those of you who know Kubernetes a little better, they might say, that's kind of stupid doing that, right? I mean, Kubernetes brings you certain infrastructure components already out of the box. So we can simplify this here quite a lot. To this here. We don't need a key value store anymore. Kubernetes, for example, has something called config maps, which are a declarative way of, declaring your key value pairs. So you don't need console for this. You have the Kubernetes DNS inbuilt, so you don't need console to do the service discovery anymore, right? You have the service abstraction already in Kubernetes, you have a DNS name, and that's all you need to know. And we don't need the traffic edge server as well, because Kubernetes has something called an ingress, right? This is pretty much the same. Now, the downside, this only works in Kubernetes, right? For my demo, it's always good to move between different orchestrators and schedulers. But if you plan to go to Kubernetes or use OpenShift, then this would probably be the way you build your microservice architecture. So you don't need all those additional infrastructure components. Now, this is what a deployment definition looks like. Pretty simple YAML file. I'll show you in an editor later on. You can define resource constraints. Do this carefully. You have two types of resource constraints. The one are the requests and the one are the limits. Now the requests helps the Kubernetes scheduler to find the right worker node where to place your pod. You say, I want a quarter CPU and I need here 100 mega RAM. So it finds the right node and your pod will be scheduled on that node. So this helps the scheduler. And if there's not enough space in your cluster left, for example, if there are not enough resources, well, Kubernetes will not schedule your pod. So it will not overload your system. And the limits, they are checked by Kubernetes. So if you have a memory leak, maybe in a native application, and your system exceeds or your pod exceeds this memory limit, for example, then Kubernetes will kill it and restart it. Liveness and readiness probes. This is what Kubernetes uses to, well, to see, can I already divert traffic to this pod? This is the readiness probe. And is it healthy? This is the liveness probe. So in a Spring Boot world, you will give it the actuator endpoint and you're done. And this is the service. Down here, you see the selector. This is basically the service now selects any pod that has the labeled switcher service. Done. So time for demo. 13 minutes left. That's awesome. So you might ask yourself, what's this here? Okay. So this is a programmable MIDI controller. And what it does, it visualizes deployments and pods. Okay, so every row is one deployment. And every button in one row is one pod instance. Okay? So when I operate now on the console a little, then you will see, hopefully see that things change here. So, no slides. Go to the console. So the first thing I want to show you is, oh wait, let's kill this one here. Okay, so what I want to do is I use kube control, that's the CLI. I say apply -f, and I apply the switcher service YAML. So service created, deployment created. Maybe I need to restart things here. Yes, demo. So in the meantime, I already kube control apply -f kube control switcher board. So now what I can do now, for example, kube control scale deployment switcher service minus replicas equals 4. Okay. Of course, you have a nice fancy UI for this as well. Cluster info, kube control cluster info. Let's go here. So of course, this is now my cluster. You see here, I have the nodes I have. So this is a 5-node cluster I spun up on Google Compute Engine last night. Here you have the services I've already created. Here are the deployments I've already created. So no one to match the following predicates. Oh, okay, see? So it already said here the switcher service is in an error state. It could not deploy 4 instances. Well, never mind. What we can do is, well, we shut down 2. So let's see if that kind of worked. Kube control get pods. So this is what it does. And now we watch it. Now, This is now the fun part of the demo, where I can start playing around with this. Well, I don't know which one which is, but have a look at the pods up there. So I can kind of create things, right? I can stop things. So this is the modern age of DevOps, right? You all need one of those MIDI controllers, right? If your angry customer calls, it's like, wow, bloody hell, my system is not running. Do something. Yeah. You roll over in your bed and you press a few buttons and you're done. So you see, and this is now the magic of Kubernetes, right? It takes care of all this, of all those things. Now, 9 minutes, so that's good. What we can do is, for example, you see here, I have a small node application. What I want to show you is a rolling upgrade. So imagine you have version 3.3 running. I need a kube control, get parts -3, all white. Did you see that down there, the output changed, where it's Auf Wiedersehen CCon 2017? So that was like the image from a previous talk in Hamburg I did. So this was like the last thing where I said, I had the last session, I only had 30 people, and then I said, oh, okay, yeah, bye-bye CCon, it was a nice conference. So let's assume this is our current version, and of course I have prepared a new DevOps Poland version. So all I do up here is kube control set image, and from my switcher node application, I just upgrade the version up there. So image updated, and in the middle you see now that it starts terminating and running, and down there you see now you have a mixed, you have some traffic going to the old version, some traffic going to the new version, and at some point when Kubernetes decides that all the new versions are healthy, it will kill all the rest, and rolling upgrade is done, okay? What you can do is kube control, roll out history, deployment, switcher node. So those are the things I can do. And if your customer calls again and says, oh, what did you do? The wrong image. Undo. Then what you can do, kube control, roll out undo, deployment, switcher node, up, and off you go. One call, and let's see if that works again. So at some point, you will see down there, we're back to the old version again, right? So this is how operating a modern cloud-native application should look like, right? No deployments for half a day. This is how deployment should be done in 2017 and onwards. Good, but we're in the wrong conference, so I reset the old image. Good. Okay. So 6 minutes 40 left. That's really good. So back to the slides. So now this was, I admit, a very short introduction to a quite complex topic, but it does feel like magic, right? This is seriously, if you do this the first time, I promise you, you will have a smile on your face, right? Because it just works, right? I have to smile every time. It's a little thrilling doing those things, but it kind of worked, the demo, and the network was stable. So, of course, it's not magic, right? I mean, be serious, it's complex technology. And implementing distributed systems has always been hard, and it's still kind of hard, okay? There's a lot to know. A lot of moving parts, a lot of technology to know. You need to get it right, right? Corba, RMI, RPC, whatever, those are the old times. Now in the new times, you have microservices and loads technology around this. It's complex. And the cloud native stack tries to help you here and tries to hide most of the complexity. But don't be fooled by the abstractions. If things don't work, you have to go into those abstractions. And this is then when it starts to get ugly, right? If you have the 3-level Docker overlay network and you don't know which IP address is talking to which one, yeah, have fun debugging that one. So it can get nasty, okay? So this is the boon and bane of the high abstractions in software development. Always has been, right? If your component wiring in Spring Cloud doesn't work for all this magic, you know, then you have to know how things work as well. So this is always what it has been. So developers and architects, we need to have additional skills and know-how. We need to go to conferences. We need to read articles. We maybe need to implement a few proof of concepts ourselves. You know, if I have some spare time on the couch, then I invite you to maybe implement a small, well, microservice and then stick it into Docker and then maybe stick it into Minikube just to get the first feeling of it, right? And for the organizations and companies, I would say, well, do it slowly. Do the transition gradually and no big bang cloud migrations. I've had customers, they say, well, old data center, we don't need this. We throw all the hardware away, we go to Amazon, and we do OpenShift, and we do microservices now. And all the developers in this organization, they say, what? I mean, this is so much, how should we change? So I have this feeling that this is 5 steps ahead too much, right? So do it slowly. First mini application, bring this one into production, get safe, so that you have the confidence in this new technology in the first place. And once you have that, you can then go large scale. So this is my advice. So please vote for this session if you liked it, which I hope. Thanks, and question.